The NP chart is a control chart for the number of defective units. In this lesson, we calculate the control limits using the normal distribution. And hello again to this lesson, which essentially has two learning objectives. At the end, you should be able to calculate the control limits using the normal distribution. And you should be able to implement this knowledge in a control chart and interpret it. This lesson is divided into two chapters. In the first chapter, we will use the normal distribution to calculate the control limits for a non-interference probability of 99.73%. And in the second, enter this limit in the control chart and discuss how it is to be interpreted. This picture shows the relationship between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics, shown on the left, can be divided into two different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. But we don't want to go into detail about them here. Second, there are the attributive characteristics. Those are all characteristics that can only be counted. On the right side, we have the different control charts for attributive characteristics with a white background. As you can see, there are 6 control charts for attributive characteristics. As already mentioned, this is about the NP chart for the number of defective units. Let's start with the calculation of the control limits using the normal distribution. The diameter of this piston is our example. Although this is a variable characteristic, it can also be checked attributively. For example, with the limit snap gauge. The test result is therefore only a statement as to whether the diameter is within the tolerance or not. So just a statement of pass or fail, or accepted or rejected. The results of the tests are shown on the table on the right. A sample size of 500 parts was tested each day. This was done for 100 consecutive days. A total of 493 non-conforming parts were found. To calculate the control limits, we need the formulas shown on the left for the upper and lower control limits. Let's start with the formula below. It is used to calculate the proportion of defective units, P, in a sample. Xi is the number of defective parts in a sample and N is the sample size. P bar is the average of the individual defective proportion in a sample. With a variable sample size, the different proportions must be taken into account when calculating P bar. For the sake of simplicity, we leave the sample size N constant in our example. As already mentioned, LCL and UCL are the lower and upper control limits for the number of defective units. U for 1 minus alpha half is the quantile of the standard normal distribution. Since this training is aimed at advanced users, it is assumed at this point that you have the appropriate knowledge of the standard normal distribution and what is meant by quantiles and how they are calculated. Separate lessons are also available for this. The average proportion of defective parts is required for the further calculation of the control limits. With a constant sample size, this is calculated from the sum of all defective parts found divided by the number of all tested parts. Thus, P bar is 0.0098. Translated, this means that approximately 1% of all parts in the sample do not meet the specification. The average number of defective parts is also required for the further calculation of the control limits. This is calculated from the sample size and the average proportion of defective parts P bar. The average number of defective pistons is therefore 4.93. Next, we need the quantile U of the standard normal distribution for a non-interference probability of 99.73%. There are a table for these in relevant books or on the internet. A small excerpt from such a table is shown here on the right. If you want to know more about these tables or how you can calculate these quantiles yourself, you should take a look at the separate lessons on this topic. We chose a non-interference probability of 99.73%. This also corresponds to the range of plus minus 3 times the standard deviation, hence 6 sigma. In relation to the upper bell curve, this means that it can be expected that all values will be between the value x lower and x upper with a probability of 99.73%. For 99.73%, the quantile U is 3. This value has already been inserted into the calculation in the middle. With 3 for U, P bar, an average proportion of defectives of 0.0098 and the mean sample size of N500, the value 11 is calculated for the upper control limit. A negative value is calculated for the lower control limit. Therefore, the lower control limit does not apply here. So, now that we have determined the upper control limit, we now come to the creation and interpretation of the NP chart. In the control chart on the right, the number of defective parts in a sample is entered on the y-axis. The x-axis is for the sample size. In our example, it is days because one sample was taken per day. The average number of non-conforming parts, NP bar, was entered into the control chart as a kind of middle line of the value distribution and is at the known 4.93. The upper control limit was drawn at the calculated 11. The red value curve shows the data on the basis of which we carried out our calculations. It is therefore to be expected that all values will be below the upper control limit with a probability of 99.73%. The probability that one of the values is above the control limit is less than 0.27%. If such a rare event occurs, it is an indication that the process is no longer under control. The cause must then be determined and the process readjusted if necessary. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The control limits of the NP chart for number of non-conforming units are calculated using the normal distribution. The non-interference probability in the process is 99.73%, which is equal to a 6 sigma range. One or more values above the upper control limit is an indication of an out-of-control process, which may then have to be readjusted. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye.